Welcome to the Architecture Teardown. Today, we are analyzing the Phase 2 backend of AgrowCart, looking at how the engineering team structured the data flow. The central engineering problem here is bridging a massive digital divide. We have to build a system accessible enough for a user with limited connectivity, but robust enough to handle high-frequency enterprise commodity trading. A standard CRUD application will fail under these conditions. True agricultural technology requires enterprise-grade architecture to process real-time variables. We are looking at the specific stack chosen to solve this gap: Next.js 15, WebAuthn cryptography, a strict MongoDB access schema, and a standalone socket I/O cluster. To strip away digital friction, the team deployed an edge-rendered passwordless architecture that moves heavy computation off the device and onto the node. This shows our primary user, a farmer manually harvesting millet. At this stage, users face severe information asymmetry and rigid digital literacy barriers. This image reveals our secondary user group, Rural Women-Led Cooperatives, or SHGs. These users require communal financial routing, completely breaking standard individualistic user models. This final image shows the end of the chain, premium sorted millet grains. Here, industrial buyers demand high-volume precision data and end-to-end traceability. A traditional monolithic MVC framework cannot bridge this gap. You cannot successfully serve the exact same heavy client application to a degraded rural network and a high-frequency trading desk. The architecture must handle intermittent 3G connections and live B2B trading simultaneously. Standardizing this stack is a matter of system survival. This diagram outlines the transition away from traditional client-side rendering. For the farmer and SHG modules, we utilize Next.js 15 server components. Instead of sending heavy JavaScript bundles, server components strip the logic at the edge node, sending only pure HTML to the user's device. Because the device receives lightweight HTML, the time-to-interactive metric drops significantly. The interface becomes responsive almost instantly, even on degraded rural bandwidth. If the connection drops entirely while the farmer is in the field, the React 19 architecture implements optimistic UI updates. The application registers the user's input locally and syncs with the server the moment connectivity returns. Deploying the Next.js app router reduces the data overhead to a fraction of traditional React apps, allowing the marketplace to function on the edge of the network. Traditional password resets and email verification loops cause catastrophic drop-off rates in rural demographics. This schematic illustrates our authentication overhaul. We replaced standard database hash verification with Nextauth and WebAuthn, deploying device-level passkeys. The device's secure enclave generates a public and private key pair. The server stores only the public key, permanently removing shared secrets from the database. A farmer authenticates using only their local fingerprint or device PIN. The complex cryptographic exchange is entirely abstracted away from the user interface. By utilizing native device hardware for authentication, we eliminate phishing vectors and transform a severe user friction point into an enterprise-grade security protocol. Moving down the stack, we reach the data layer and the Mongoose schema design for the MongoDB cluster. This database tree shows our strict role-based access control model. We must unify farmers, SHGs, and processors into a single database without leaking read or write permissions between these entirely different operational profiles. For the processor portal, the schema requires tracking an industrial ledger. Every batch of value-added millets must be logged and traced from origin. We integrated an automated FSSAI gatekeeper directly into this schema, a strict Boolean validation field tied to food safety compliance. The database middleware actively monitors all batch logging operations. If the processor's FSSAI license field is unverified, the write request is immediately rejected before the data is committed. This architectural choice shifts regulatory compliance to the very beginning of the pipeline. It replaces retroactive human paperwork audits with an immutable cryptographic runtime gatekeeper. The final Phase 2 requirement is facilitating live, real-time bidding and negotiation between B2B buyers and SHG collectives. Running persistent WebSocket connections directly through the primary Next.js serverless API routes creates massive vulnerability. It risks connection pool exhaustion across the entire platform. This topological map shows the physical isolation of our traffic. Standard REST API calls route to Next.js on port 3000, while live bidding data routes strictly to a standalone Node.js and Socket.io cluster running on port 4000. This architectural decoupling isolates the heavy, concurrent load of active trading. It protects the primary marketplace from latency spikes or connection crashes. Isolating state transport guarantees microsecond latency for live B2B negotiations, leaving the main agricultural application lightweight, highly available, and fully optimized for search engines. This blueprint illustrates the fully integrated state of the system. We have the WebAuthn client, Next.js edge routing, strict Mongoose RBAC, and the decoupled socket node all running in parallel. This backend architecture handles the heavy processing and security handshakes, leaving the rural user to interact with a clean, responsive interface. With Phase 2 locked, this resilient foundation is ready to absorb the extreme data demands of Phase 3, which will include Gemini AI analysis modules, complex payment pipelines, and immutable blockchain ledgers. Ultimately, AgrowCart is a rigidly engineered, distributed system blueprint designed to fully digitize and scale India's rural agricultural economy.